All right, so we're looking at showing that this infinite family of solutions is a set of solutions for this differential equation. So as before, we just want to find y and y prime, substitute them into the ODE here, and then show that we get an identity. So we already know what y is. It's right here. In fact, I'm not going to rewrite it. Let's just write y prime. Y prime would be 4x. This goes to 0, and this right here is going to become minus 4x 4x times c. Let's write it like that. 4xc e to the negative 2x squared. Normally I'd actually want the c over here because it's a constant, but whatever. So let's substitute this in to that differential equation. Y prime shows up first. So we have 4x minus 4xc plus 4xy. That's 4x times this general solution. 2x squared minus 1 plus c e to the negative 2x squared. Distribute your 4x in. We have 4x minus 4xc plus 4x times 2x squared. That's 8x cubed minus 4x plus 4x times this. That's going to be 4xc e to the negative 2x squared. Notice, I'm missing my e to the negative 2x squared here, so that should be right there. Forgot to write that in. A little bit sloppy, but whatever. So this term and this term will cancel. This term and this term will cancel, and we're left with just 8x cubed. Making that substitution in my DE here gives me the 8x cubed that I'm expecting to find. So the steps here feel very familiar to what we did in that previous example, and that's because those two examples that we checked were both members of the same family of solutions here. Notice also, this family of solutions has only one parameter. That's c right there. And it has one parameter because this is a first order equation. Down here, we're doing another example, and this time we're looking at a third order differential equation because that's the highest derivative that I see. Notice the family of solutions that we're going to check has three parameters. Three matching the order of this differential equation. Okay, so now if we want to verify that this is a family of solutions to this big differential equation here, I need to calculate all the way up to my third derivative. Notice also in this case, x is no longer being playing the role of the independent variable. X is actually the dependent variable this time, and t is my independent variable. I want to mix it up a little bit just so you don't get too used to x being an independent variable. So we have x already. Let's find x prime. X prime is going to be negative c1 t to the negative 2 plus c2 plus, we need a product rule here, so this is going to be plus c3. Product rule is going to give me the natural log of t plus t times 1 over t, which is just 1. And then here I'm going to get plus 8t. Okay? All right. Let's differentiate this again because we need a second derivative now. This is going to give me 2c1t to the negative third power. That's a constant. That's going to go away. The derivative would be 1 over t, so I'm going to get plus c3 over t after differentiating, plus 8. Okay? I also need x triple prime. X triple prime will be negative 6c1t to the negative fourth power. And then this will become minus c3 over t squared. And that's going to go to 0. Okay? So this one gets a little messier because we have so much that we're dealing with. I used prime notation here, by the way, even though we were using Leibniz notation here. That obviously is not going to matter. It's just a little less for me to write. Let's plug these things into this third order differential equation right here. So first I have t cubed times my third derivative, which is given here. T cubed times negative 6c1 t to the negative fourth minus c3 over t squared. Let's write that as minus c3 t to the negative second power. Okay, then I have plus 2t squared times my second derivative, which is given here, 2c1 t to the negative third power plus, let's call that c3 t to the negative 1 power plus 8. Now I have minus t times my first derivative given here, negative c1 t to the negative second power plus c2. Let's do this. Let's distribute the c3 in here just so it's easier to see how things cancel later. Plus c3 natural log of t plus c3 right there. And then I have plus 8t there. Okay, and then I have this plus x right here, but this is what we're calling x. So I'm actually kind of running out of space here. I'm going to write this down here. Plus x, which is this guy. c1 t to the negative 1 power plus c2 t plus c3 t natural log of t plus 4t squared. Okay, now I clearly don't have enough space, so I'm going to kind of continue this on to another page. Let's move that down a little bit. I need to zoom out a little bit, don't I? There we go. Sorry if some of that was cut off. So there's a lot of simplification that needs to happen here. I have some distributive stuff to do. So distributing this in, t cubed times this guy, that's going to give me negative 6 c1 t to the negative 1 power minus c3 t. Distributing the 2t squared in here, I should get plus 4 c1 t to the negative 1 power. And then I'm going to get, what's this, plus 2c3t, right? Is that right? Yeah. Plus 16t squared. Distribute my negative t into all of this mess, minus, well, that's going to actually become plus c1 t to the negative 1 minus c2t plus, nope, sorry, that's a minus right there, minus c3t natural log of t minus again c3t minus 8t squared, and then down here I have all of this stuff. Plus c1 t to the negative 1 plus c2t plus c3 plus natural log of t plus 4t squared. Holy moly, that's a lot, right? So now what we're doing is we're looking for things that cancel, because hopefully a whole bunch of stuff will cancel. In fact, looking at what this is supposed to come out to up here, we're hoping that everything except for a 12t squared cancels out. So cross our fingers, hope we didn't make any mistakes, and then let's look for cancellation. So I have negative c3t natural log of t here, and then I have a this is a t right here, not a plus. I have a positive c3t natural log of t. So these guys cancel out. That's good. That's something. Let's look for maybe our t to the negative 1 powers. I have a t to the negative 1 here with a coefficient of negative 6, another one with a coefficient of 4. Here I have one with a coefficient of 1, c1, and then another one, c1. So actually, negative 6c1 plus 4c1 plus c1 plus c1, all of that's going to cancel out because I have negative 6 plus 6 here. So that's a lot. Canceling out, that's good. Let's take a look at the t's. I have a negative c3t, positive 2 c3t, so I'm up to c3t, combining those. Let's see. Here's a minus c3t, so those are actually all going to cancel. This guy, this guy, and this guy. Those are gone. I have a negative C2t and a positive C2t right there. Looks like a just about... Okay, no, here we've got 16t squared minus 8t squared. That puts us at 8t squared plus 4t squared. That all adds up to 12t squared. So this is equal to 12t squared. Nice. That's what we were hoping to have happen, right? Because we wanted this to come out to 12t squared. Now, that was obviously a lot of algebra. And for the most part, I'm not going to walk through all of those little algebraic steps, even though you do need to do that when you're verifying, and it's just kind of for the sake of time. This isn't an algebra class, so big, algebraic simplifications like this aren't anything you haven't seen before. But I wanted to at least do it once to sort of give you a feel for what verifying a solution like this actually feels like. Okay, so we are in good shape here. Let's go ahead and move on. All right. So what we're showing here, a family of solutions to an ODE will typically consist of infinitely many solutions, as we see here. There's also, because there's an infinite number of solutions in a family of solutions, that means you also have an infinite number of solution curves. So in the previous example, this first family of solutions to the ODE, if I plug in several different values for this parameter, -3, -2, -1, 0, 1, 2, 3, just some selection of real numbers, and I plot the solution curve for each one of those, these are actually those solution curves for that specific example. And there's more, right? There should be infinitely many, but I picked sort of a sample of them. Now, it can happen that when we're looking for solutions of a differential equation, and we find a family of solutions to that differential equation, it's possible that the differential equation may have even more solutions outside of that n-parameter family. And if we're able to find such solutions, such extra solutions, we call them singular solutions. So here's an example, and again, I'm not going to verify this, I'm going to let you verify it just for practice. But suppose we're working with the ODE dy dx equals y minus 3 quantity squared. This is his first order differential equation. You can verify just by, again, doing the method that we've been doing, that this function right here, y equals 3 minus 1 over x plus c, is a family, the c being the parameter here, a one parameter family of solutions to this differential equation. Try it out, see if you can verify. But the constant function y equals 3 is actually also a solution to this. This one you can verify just by inspection. Plug this function into the differential equation. I have a y showing up here. If y equals 3, this becomes 3 minus 3 squared. That's 0 on this side. If I plug something into my dy dx here, I use the derivative of this function. Being a constant function, its derivative is 0. So I also get a 0 on the left-hand side. Clearly, this is a solution to this differential equation. However, this particular solution here does not belong to this family of solutions, because there is no value of c that you can plug into this denominator so that this becomes a 3. See if you can verify why that's the case. Okay, we're getting close to being done with 1.1 here, just a little bit more to talk about. You may recall from Calculus 2 your instructor briefly talking about the fact that some functions just flat out don't have antiderivatives. When you're trying to solve some tricky kind of integral, you're generally looking for an antiderivative. But certain functions just don't have them. Or to be a little bit more specific, we call them elementary antiderivatives, meaning an antiderivative that's expressible in elementary functions. Those are exponential functions, polynomials, trigonometric functions, hyperbolic trig functions, all of the functions that you're kind of used to seeing up until this point. It can happen that when solving a differential equation, you may have to look at an integral of a function that has no elementary antiderivative. And in those cases, you're going to basically feel stuck. So that's not actually a problem most of the time, because again, kind of like how we were satisfied leaving certain solutions in implicit form, Other times, we're going to just be satisfied leaving a solution to a differential equation in integral form. So to give you an example, we're looking at this differential equation, y prime plus 2xy equals 1. And we are going to verify that this is a solution to that differential equation. Notice there's an integral showing up here. Now, e to the negative t squared dt. If you try to integrate that, this is an example of a function that does not have an elementary antiderivative. So we're not really going to be able to solve this integral directly. Instead, we're just going to let it live in our representation for our solution. How do we verify that this thing is a solution to this differential equation, though? Well, I need y prime to be able to plug into this. So let's start there. What is y prime? Okay, y prime is the derivative of this. So if I take this derivative, that's going to become negative 2x e to the negative x squared. And then I have e to the negative x squared times this integral. So I need my product rule. Let's start with the derivative of the first guy here. Negative 2x e to the negative x squared times that integral. 0 to x e to the negative t squared dt. Plus the derivative of that second function times the first. And you're going to notice this a lot. My pluses and my t's look very similar. Try to keep track of which is which. I get confused sometimes myself. I think I need to figure out a better way to write my t's. Anyways, what is the derivative of this second function? Well, let me actually start by just writing the first function, e to the negative x squared. What is the derivative of this with respect to x? Well, you should remember seeing integrals of this form, where you have your limits of integration going from some fixed value, some constant, to your variable x. If you differentiate this with respect to x, the fundamental theorem of calculus tells you how to do that. The derivative of this with respect to x is just the integrand with an x replacing the t. So this becomes times e to the negative x squared. Okay? Now, I need to plug this thing in. In fact, let me simplify that a little bit. I can write that as negative 2x e to the negative x squared minus 2x e to the negative x squared times that integral, 0 to x e to the negative t squared dt. I can multiply these two by adding those. This becomes plus e to the negative 2x squared right there. All right. Plug this in to our differential equation up here. I'm going to get y prime, which is this, negative 2x e to the negative x squared minus 2x e to the negative x squared times the integral, 0 to x e to the negative t squared dt, plus e to the negative 2x squared there. Okay, plus 2xy. So plus 2x times this, e to the negative x squared plus e to the negative x squared times the integral from 0 to x, e to the negative t squared dt. Okay, distribute that in. And let's try to kill a couple of birds with one stone here. So I see that 2x times e to the negative x squared is going to cancel with this negative x e to the negative x squared. So I can cancel that with that guy. I'm going to multiply this 2x into here, and I'm going to get a 2x times e to the negative x squared times that integral. That'll be a positive. This is a negative. That's going to cancel with that guy. So I get all this cancellation happening here. Okay? All right, now I'm left with this e to the negative 2x squared. I should be left with a 1, so that means I think I did something incorrect here. Let me check, make sure something didn't go wrong.